We tend to think of the internet as an invisible cloud. We make video calls, stream high-definition movies, and pull data from the air, experiencing global communication as a frictionless wireless process. The reality is much heavier. Every time you send an email across the world, your data travels as physical flashes of light, confined inside solid glass threads thinner than a human hair, resting deep on the ocean floor. This physical reality took shape in 1988 with the TAT-8 transatlantic line. That project proved we could fire pulses of light beneath the sea to connect continents, marking the start of a global transition to fiber optics. Maintaining this infrastructure requires massive investment. Tech giants like Google, Meta, and Microsoft actively co-own the subsea lines that anchor the planetary network. Building this network requires us to transform common quartz sand into flawless glass, a material that must survive the crushing, freezing conditions of the deep sea. The physical internet starts here. Heavy tracked excavators tear into deposits of pure white quartz sand, loading dozens of tons of earth into trucks. This sand is full of clay, stones, and organic debris. To strip away these impurities, the material undergoes a multi-stage purification. It is blasted with high-pressure water, baked in industrial furnaces, and vaporized into gaseous chemical compounds. This effort is poured into creating a dense, solid glass rod, known as the preform. Because the purity requirements are absolute, this specific stage takes dozens of hours and is the most expensive step in the entire manufacturing pipeline. Instead of melting sand, engineers build the glass layer by layer. Inside a rotating tube, hot gases react. Microscopic silica particles fuse to the inner walls. By adjusting the chemical recipe, technicians dictate the glass structure. Outer layers form a reflective cladding to trap the signal. Inner layers form the core, the physical path for data. This exhaustive chemical processing solves the purity problem, condensing tons of rough earth into a single flawless glass rod. The rod is hoisted to the top of a 60-foot drawing tower and fed into a furnace burning at nearly 3,600 degrees Fahrenheit. The bottom of the glass softens, and a single glowing drop falls, pulling a continuous thread behind it. As the thread is drawn toward the base of the tower, it reaches a uniform diameter of exactly 0.005 inches. This dimension is critical. Laser sensors scan the thread continuously. If the strand deviates by even 1,000th of an inch, the light will scatter, and that section of the fiber is immediately cut away. Freshly drawn glass is highly fragile. Before reaching the base of the tower, it runs through a bath of liquid polymer and gets blasted with ultraviolet light, instantly curing a protective jacket around the bare silica. From a rigid 3-foot rod, the factory has drawn dozens of miles of light-carrying thread. But even with this polymer skin, the fiber is still too delicate to survive outside. To survive deployment, the delicate strands enter the heavy industrial cabling phase. Fibers are gathered into bundles, surrounded by waterproof gels, and wrapped in lightweight Kevlar. In this cross-section, you can see the fiber bundles buried deep in the center, encased by dense rings of rigid plastic and thick steel wiring. These layers are designed to deflect ship anchors and withstand the immense weight of the ocean. Before it leaves the facility, the finished cable is stretched, bent, and run through thermal chambers, cycling from deep freeze to intense heat. Engineers simulate deep-sea crushing loads in high-pressure tanks, while monitoring live data streams for any sign of signal loss. Hundreds of miles of cable are wound onto massive drums and prepared for the ocean. They are loaded into specialized telecom ships, engineered to deploy thousands of tons of infrastructure. Out at sea, the ship feeds the line through tension control devices. In shallower waters, remote plowing machines are dragged along the bottom, carving deep trenches to bury the line safely beneath the seabed. The entire supply chain, from the woven Kevlar to the fleets of ocean vessels, functions as a massive, expensive shield for a single beam of light. Sitting in total darkness and crushing pressure miles below the surface, that microscopic glass core performs its job flawlessly. Modern communication speed depends entirely on these physical lifelines holding together across the ocean floor. It is the result of excavating raw sand, executing high-temperature chemical purification, and laying armored steel at the bottom of the sea. The digital age is built on the back of heavy industry, an industrial feat that turns common materials into a highway for light.